All right. Hello. So we're going to be creating a slot machine application. I'm going to try to make this as brief as possible because I know it can get a bit talkative. We're already there. So I have a folder here, just slot machine. We're going to create a file here called contract.py. And we're going to import to start the arg4 contract, arg4 library in case we need it. And also from arg4, I like to get API method directly. We're going to need subroutines, transaction, group transaction, inner transaction, and box maps. Anything else we'll import as we go. We will also need the byte arg4 class. So we'll call this contract slot machine. Pass in the arg4 contract type. Initialize. And return none. For the global states, we're going to need the VRF app, and we're going to need, we're going to call this slot machine user instance. So it'll be a box map with the accounts, which we need to import from AlgoPy, and the arg4 UN64 type. Key prefix, I'm going to leave empty. I know key prefixes can sometimes be helpful. I know there's a new endpoint coming out where you can fetch boxes according to a key prefix. Not sure where that development is, but for our purposes, we do not need a key prefix. Regarding the VRF app, you can Google usage and best practices for randomness beacon, and you'll find this article here. The ID is right here for testnet, which we'll be using. So we can just pop this in here. We'll need to import application. And that's pretty much it for global states. For our first AVI method, we're just going to test the VRF, not do much else. And we'll return bytes, which we also need to import. Just so you can see, maybe I can briefly explain how the VRF works. I won't get into the cryptography behind it. I'm just going to show you an implementation and how to actually use this. So for an inner transaction to the VRF application, you will need to import API call. And this allows you to use a method signature as an argument, which I'll show you here. So for example, in the documentation for the VRF, we're going to use this. This is the method signature. So must get, it fails if it doesn't fetch the pseudo-random output successfully. Must get accepts a UN64 and a byte array. The UN64 is the chosen VRF output round. So the round you commit to in the future where you will get the output. And the byte array is any other constant or arbitrary bytes you want to use as input to the VRF. Changing the round will give you a different output, and inputting different bytes as a second argument will also get you a different output. So if I do the same round 3 times with the same byte array, I will get the same output pseudo-random byte array. So keep that in mind. Usually as input bytes, as a constant, people choose the address of the sender as bytes instead of something like, you could also use something like a counter, right? Something that's always incrementing will never be the same. But definitely you don't want to get 2 VRF outputs at the same round with the same byte array. If you want that to be an option where they can use the same round, then you'll need something like a counter to add to the address bytes so that there is some variation. Otherwise, you're going to get 2 output bytes. If there's a favorable pseudo-random value, someone wants to use it again, this is going to fire, what's the term? Fire back, bite you in the butt. Just don't, make sure these 2 values are different every time, right? So anyways, this is the method signature. So we're going to copy this And this is going to be the first argument here. And we're also going to need to pass in the round. So for testing purposes, don't do this. Just for testing purposes, we're just going to go straight back 10 rounds, right? And something I'll quickly note, well, I'll explain this first. So the reason you don't want to do this is because the output bytes, the pseudo-random output bytes from 10 rounds ago is already known. So someone can call the VRF themselves for this round before calling this method and gets the output. So I'll call the VRF with a round, 10 rounds in the past, get the output and say, hey, that was a favorable output. Let me now call this user, this platform's test VRF method, because I know the output bytes will be in my favor. So don't use a round in the past. Always use a round in the future. So when we actually get out of this test method and start actually writing the method, we're going to be using the current round. And the VRF output won't be available until 8 rounds, the next interval of 8. So I'll get into this. So the bytes that we're passing in that I explained for some variation will be this constant here, the transaction sender.bytes. As long as the round and the byte array never match, you're good to go. And the results, the resulting byte array will go into this value here, the result variable. And the actual transaction, the ABI call object itself, is here. Okay, so we're going to return the results. And we also, as the last argument, we need to pass in the VRF app ID, which is in our global state here. And this is good. One thing I'm thinking about is if we're using the current round and the output is also for the current round. So that's something I'm going to try to keep in mind. Not JavaScript. Make sure current round is not a new VRF round, because if the current round is making a VRF, it is now part of the new VRF round interval. Let's say the next VRF output will be at round 200. And then when we call this method, assuming we're using just global.round, we are also at round 200. So the VRF is available at this round, and we're now getting the VRF output for that round. So you're not really committing to the future, you're committing to a round that's currently available. So someone could simulate this call for the current round to the VRF, see if it's favorable, and then actually call it. So this is something we'll need to do, like some modulo 8 stuff and increment, but I'll show you that afterwards. For now, we're just going to subtract like 10 for testing purposes. And I'll move this down, just ignore this for now. So we can now compile this. AlgoKit compile pi. I don't use AlgoKit. AlgoKit is really beneficial for debugging, and the fixtures are good for testing. I just like writing all my tests from scratch, and so I only use the terminal commands, but I don't actually instantiate an AlgoKit project. But if you know how, or you want to explore how to do that, I definitely would recommend it. I wouldn't just, go all out and do what I'm doing if you're genuinely trying to learn. But let's see, this should be good. So AlgoKit compile, name of the file, and we're going to add this flag because we want an arc56 schema to pop out. And we also want the out directory to be a folder called contract files, so that it's not too messy here at the root of this folder. So this should be good. We might get an error too. Let's see. Dun, dun, dun. I already know that there's going to be an error for this. So you need to indicate the return type after the ABI call like this in brackets. And it looks like this was actually, yeah. So that's the exact error that I got. So now we should be good. Just give it a moment to compile and we're good. So we can now write our testing file. So I'm going to start off with generating accounts. So just, and I number my files so you know they're in linear order in workflow, for workflow. So from algo_sdk.generate account or algo_sdk.account, import generate account, and sk or private key and pk public key is equal to the result of generate account returns a tuple with the private key and account address. And we're going to throw this into a dot end. So load dot end. And after we get these two values, we're going to set the key at our dot end to sk, value to set, sk, and then the same for pk. So sk is private key, don't confuse it with pk, pk is public key. And we're good here. Let's run this, and we should see that end pop up. I'm not scared about showing you this. I will abandon this account very shortly, but you can go to bank.testnet.algorand.network and get this account funded with 10 Algorand. And we're now good to deploy. For deployment, I like to create constants.py. So from algokit utils, we're going to need the Algorand clients. That's actually pretty much it. Oh, signing account. And we're going to load our .env. So we can grab, using the OS library or module, sk and pk. And we'll define our signing account, which takes the address, which is pk, and the private key, which is sk. And just to make this more organized, I'll switch those. So for deploying the application, we're going to need to go into those contract files, which actually doesn't currently contain the clients. And the client, and I'm just going to create a terminal command text. So the first one we used was this one. And just remove this. And the next one we're going to use is algokit gen-pi. This generates the actual client, the typed client file for everything we need to interact with the contract. So algokit gen-pi input file is going to be contract file slash, it's going to be slotmachine.arc56.json. And the output, we're just going to call it slot machine client.py. And this actually conflicts with the actual client, but it doesn't really conflict. We'll be fine. Let's just make sure this is going to work. Cool. And I want this to be in a client folder. I don't know why. I just do. Clients. And I assume it will create a folder for me. Nope, it will not. Cool. So now we have this clients folder with this client in it. You can see it's very fancy and complex. They worked very hard on this client generator at the foundation. So I don't need this duplicate anymore. And back to deployment. So yeah, constants. From clients.slotmachine_client, I'm going to import the slot machine client, slot machine factory. We're going to need the source map And I believe that's actually pretty much it. So the slot machine factory, and we need Algorand here, create an instance of a client. So slot machine factory is needed for deployment, and this just needs our Algorand clients, our sender, which is going to be sending account address, our default signer, sending account.signer, and then we need a, it's actually it. So just these 4 things. The client will need an additional parameter called approval source map, which I will show you that after we actually deploy it. But this slot machine factory we'll use for deployment. I don't think we need to, yeah. So we're also going to need to fund the contract with its account minimum balance requirement, which is 0.1 Algorand. So we're going to need the parameters for payment transactions. And then from constants, we're going to import our Algorand client, which we've already instantiated in constants, and the slot machine factory. So slot machine client, deployment response, or this would better be suited as transaction. No, deployment response is fine. The reason I hesitate is because for the factory there is a deploy method, but I don't use it because it tries to recycle previous contracts, which sometimes conflicts with what I'm trying to do. So if it finds that the approval program matches byte for byte, it won't actually deploy a new instance, which I think is a little weird. And it just returns the same app ID, which is not what I want. So I use send.create.there, and it's kind of like a way to bypass the eco-friendly method of deploy, which kind of can sometimes clash with what you're actually trying to do. So that's creation, and then a print statement would be nice. So deploying slot machine application ... and then slot machine application created, and we will pass in here the app ID, and we'll maybe be more clear here, app ID. And then another print statement, funding application minimum balance requirement with minimum balance requirement for accounts MBR. This is worded a little bit weirdly. Funding application. This is fine. I'm not going to go crazy over it. And now we can create our payment transaction, which we can actually send directly from our Algorand client. Payments, params, payment params, and the sender is our signing account address, which we can import here. Signing account address, signer, signing account signer. The receiver is going to be the created client app address, and the amounts, algo 0.1 is what's needed. And there's a validity window parameter that I like using. If you sequentially create transaction after transaction and you're actually waiting in between for confirmations, you will eventually go outside of the default validity window, which I used to think was 100 realms, but if you do this like 3 times, it will probably fail here at the 3rd one. That's what I've noticed. And I think the validity window is not as large as it used to be by default. Maybe I'm going crazy, I don't know. But anyways, application funded with account MBR of 0.1 Algorand. And we're pretty much done here, aside from saving the application ID, which we'll need in the future. So load.env, let's set root here, and then we'll do set key, env, key to set is going to be app ID. And don't forget to convert this to a string. The .env does not like integers being passed into it, I believe. This is going to be slot machine client .app ID. And we should be good here. We'll just double check by actually running it. So deploying slot machine application created. Here's our app ID. And application funded, funding, application funded, and then in our .env, we now have that app ID ready to go. So we can start with our test VRF method, finally. So I'll create a new file here, test vrf.py, and now we need a way to get a client, which comes conveniently with the Algorand object here. So and I like to do this. So app ID is equal to int, because we need it as an integer, get env app ID, and then if app ID, because if you have this constants file, for whatever reason, if I like post this on GitHub, and you clone it, if you try to run any of these files, it will try to create an app client by default if I do this. So slot machine client is equal to Algorand client get typed app client by ID, and then I'll do the app ID is this app ID, and already at this point this will fail if you don't have an app ID in your .env. So if the app ID exists, then start creating a client. And default sender, same thing, address of the signing account, default signer, getting a little repetitive, that's okay. And the type client, which I prefer at the top actually, we import here from the slot machine client. And this one's a little tricky, approval source map. So we're gonna need JSON and source map we already have here, and import JSON. So it's gonna be source map JSON.loads path, which we need to import this way. So JSON.loads path, and path is wrapped around its own parentheses here. So path file parent, and we're inside of we're actually at root, so this should be fine. Oh no, the file's in here. So contract files slash slot machine.arc .approval.puya.map, and this needs to be read text, and we should be good here. If not, we'll get an error. And now we have a way to get the slot machine clients consistently from our constants, so we don't have to type that every time. So going back to our test VRF file, we're going to need, I think just the client should be fine. Oh, we're also going to need to define some params really quickly. So there's the common app call params, and then there's send params. And I like to just define these here, so I also don't have to type this every time. So defaults common app call params is equal to common app call params. The only thing I need here is max fee, and this requires algo amounts imported. And I'm going to move this over. So here, algo amounts, and microalgo 10,000 is usually sufficient. You should be able to gauge and kind of use your intuition to figure out if this is sufficient. If you have like a lot of intertransactions, like more than 10, right? Because intertransaction fees are set to 1,000 each. So if you have more than 10, this is not going to be enough, especially if the network is busy. This will already be more than 1,000 for your outer transactions. Inner transactions are fixed at 1,000, but outer transactions, that might go up. And then we also need a default send params. And this, I just need cover app call transaction fees, the inner transaction fees, and then populate app call resources set to true. That way we don't have to put in any accounts, app, asset, or box references. The simulate call automatically detects everything. And that also requires an inner transaction fee. So going back again, finally, to our test VRF file. So we're going to need the slot machine clients and the defaults. You can only type DE before it goes to default. So slot machine clients and transaction response equals slot machine client dot send dot test VRF. There's no args here, just the params, and we imported these. So params is the default common app call params, and then send params is the default send params. And we will make a print statement here, testing VRF method, dot, dot, dot. And over here, test VRF successful. 2 L's or 1 L? I think it's 2 L's. Give me 1 second. Yeah, 1 L, cool. Test VRF method successful, and we're going to need the transaction ID, just to be tidy here if you want to check it out on LoRa. And we're also going to need the ABI return, which will just remove all of this, or output pseudo random output bytes. And this is going to be on the return property. Oh, no, ABI return. And we should be good here. So, simple enough. I think this is fine. Let's give it a spin. And it might error. Nope, it's fine. So testing VRF method, and we should see these. So this is a 32 pseudo-random byte array. And now we can get started on the slot machine. So test VRF we don't really need anymore. I'm actually just going to delete this file. Go back to our contract and comment this out. And we have our box map ready to go. Let me just put this down. So one of the concerns I had was this one here. So if the current round is equal to the next VRF round, we should probably increment by 1 so that someone can't simulate at the same time that they're calling to see if the output is favorable. It's a little tricky, but I'll get this out of the way first. So first of all, the method is called create slot machine instance, and it's going to need an MBR payment because when you write to a box, it increases the minimum balance requirement for the contract. And this is going to be a payment transaction that returns nothing. There's no need to return anything if we get a transaction ID back. It was successful. I have some logic for the MPR payment, the MPR payment that I want to get back to. But just to go over the VRF round thing I was just talking about. So the next VRF round is going to be, for example, if you're at round 101, VRF rounds occur every interval of 8. So if you're at round 101, the next VRF round would be 108. So assuming, like just for the math, the current round is 101. The next VRF round is 108, and you can get that output by doing the current round plus 8 modulo 8. And you get the difference between 8 rounds in the future and the next VRF round. So 101 plus 8 is a 109. 9 modulo 8 is 1. So next VRF round will be the global.round plus 8 minus the current round plus 8 modulo 8. And just in case I always feel finicky with this, I'm going to wrap this in another parentheses. So this is when the next VRF round is. So if next, because let's say we're at round 108, 108 plus 108 modulo 8, so that's 108 plus 0, which is 108. That's bad. So if next VRF round is equal to the current round, the next VRF round is equal to next VRF round plus 1, right? So this looks a little complicated. It's not. But this is actually going to be changed to chosen round. Sorry, give me 1 second. Next VRF round. Okay. So if next VRF round is equal to global round, chosen round is equal to the current round plus 1. And we'll set chosen round to global.round here. And maybe we'll just do this. Yeah. This works. Now we can create our box with this chosen round. But first I want to get back to this MBR payment logic. So I usually like doing two things. One's for security, one's just general for maintaining the exact MBR balance for the contract. If your contract needs extra algo for whatever reason, or will have extra algo, for example, if it's like a staking contract, people will be sending algo to it. You can still use this method actually. Ignore what I'm saying. So look, this is a subroutine. I start off with contract is payment receiver. Because if someone is making a payment to your contract, you want to ensure that your contract is actually getting it, right? Just including the MBR payment is not enough. You want to assert that the receiver of this payment, the one defined in the payment, is the current application address. You should always double check that. Anytime you're mandating that something goes to your contract, you should actually check that you're indicated as the receiver for that transaction. So the first thing is contract is payment receiver, and pass in the MBR payment. The next thing I like to do, if the MBR will be increasing for any reason, I like to get the MBR at the beginning and end of the application call. So it's going to be global.current application address.min balance. And we're going to need to import UX64. I don't think we'll need bytes anymore. We will need these two though. So for example, I know that I'm going to be creating a slot machine user instance box map for the sender, and it's going to be equal to an arc4 UX64 instance of the chosen round. Because when you use box maps, it needs to be an arc4 type. So yeah, when I do this, I know the MBR balance is going to increase because we're using box storage. So pre-MBR is equal to self.getMBR, and then post-MBR is after we actually use the storage. Something cool about box storage, the moment that it changes, it's immediately reflected in the MBR. So the MBR cost is post-MBR, the increased MBR, minus the MBR before the MBR increased. And the excess is the MBR payment amount minus the MBR cost. And you don't need to verify that the MBR cost is greater. I'm sorry, you don't need to verify that the MBR payment amount is greater than the MBR cost unless your contract accepts algo above the minimum balance requirement. But if it does, then you should probably assert right here is greater than the MBR cost. But this would fail otherwise if your contract was always at its exact MBR balance. And then with this excess, I create another subroutine called refund excess. And this basically just accepts the excess amount and sends a payment transaction to the caller, and the amount is the excess that's passed in, and you need to submit this. So self.return or refund excess equals excess. And that's pretty much it for this method. So creating a slot machine instance basically creates a box for this account, the one calling the method, and the value to that box is the chosen round. And that's going to be used in the next method, which I'll put down here. And this is taken care of. We don't need, well, I'll keep this for a second just for use it. So the next ABI method is something called pull slot machine. So this is essentially walking up to the slot machine and pulling that lever that begins the columns start rotating through those numbers. So the three numbers that we're going to be using, so imagine a slot machine, 3 columns, one item per column. So a slot machine usually has like fruits or something, so like a banana, peach, apples, coins, something. And as it rotates, the goal is when it stops, however randomly it stops, you have 3 consecutive images or items, right? So 3 bananas, you win. 3 peaches, whatever fruit, as long as there's 3, you win. There are lots of different types of slot machines. This one just has 3 that need to match, and they're going to be fruits probably when we get into front-end integrations, which I don't know if I'm going to do in the same video. It might take way too long. I'm sure we're over 30 minutes by now, or close to it. So pull slot machine. So we're going to access the box value from the slot machine user instance of this sender. And this won't exist if they don't have a box, so we don't need to assert that transaction sender is in self.slotMachine user instance, but if you'd like, you can add that in. And this is going to be the chosen round, actually. That's what we're writing in here. Chosen round. So with this chosen round, we're going to call the VRF. And I removed bytes for some reason. I still need that. So instead of global round -10 for testing, we're going to use the chosen round. And this needs to be in a native format as an integer. I don't know if it'll error. Usually it interprets either way, but I'm just going to do this to be safe and save time. Then bytes of the sender as our input bytes. And we should be good here. But we're not going to return this 32 byte array, 32 count byte array. We're actually going to get 3 integers representing the slots that came out, right? So peaches, bananas, or tomatoes, let's say. So it's going to be a 3 by 3 slot machine. So 27 possible outcomes So you could get a banana, peach, tomato, 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 banana, whatever it is. So we have three potential values, 0, 1, or 2. So we're going to do it like this. Out of the 32 bytes, we're going to use the first 24. And we're going to do it this way. So integer 1 is going to be the first 8 bytes. Integer 2 is going to be the second 8 bytes, and integer 3 will be the third 8 bytes. And then we need to convert these into integers, and we can use this using the from bytes method of the arg4 uint64. And let me just do this for each one. And now that we have an integer, we do need 0, 1, or 2. And to perform arithmetic on an arg4 uint64, you definitely need its native format, the uint64 representation. So from here, we're going to do modulo 3 for each one. So if the number was 4, 4 modulo 3 is 1. If the number was 5, 5 modulo 3 is 2. And if the number was 6, 6 modulo 3 is 0. So you could have 0, 1, or 2. So the first slot, second slot, third slot. And these numbers, so first slot, second slot, third slot, and the 0, 1, or 2 actually refers to which fruit, right? So bananas, peaches, or I forget what the other one was, strawberries, right? And we're going to return from this method a tuple of 3 integers, actually. And let's do this here. And we're actually done, I think. The last thing I want to do is probably delete this box, so the outcome's done. So I want to get the MBR. So this is going to be post MBR and pre MBR. But since the MBR is decreasing, we're going to do this backwards. We're not actually doing this here. So here, we're going to delete the slot machine user instance for this user. So we're going to get some MBR freed up, and the free MBR is equal to pre-MBR, which is the higher amount, minus post-MBR, which is the lower amount after we delete the user's instance. And then we're going to refund access, and the access is just going to be the free MBR to the user. And that's pretty much it. So this is done. I might put these together a little bit so you know that these are pertaining to each other. And this you don't really need, but take note of this. I'll leave this here. And we're good. And now we're just going to test it out. Cool. And I'm going to remove this so no one tries that. Compile. And then we're also going to need to generate another client. Hit Control R on your keyboard, and you should get the last command similar to what you're typing. So if I did algokit compile, that's the most recent command that I did. So deploy a new instance, and we can create our create slot machine instance.py. This is going to be slot machine clients. Gonna need a signing accounts, payment params from AlgoKit utils, algo mounts. We'll need the default common app call params and default send params. And we'll see what else we need as we go, but I believe we definitely need Algorand here. I'll put it after the client. And that's to create the payment transaction. So the slot machine client, and I'll just start from here, .send, create slot machine instance. This has an args param, and we can get this from the client. Import create slot machine instance args. This makes it a bit easier to see what's going on. Now we need an MBR payment. So MBR payment is equal to algorand.create transaction, not send one immediately. We want it added to the group. Payment doesn't have any params, just put in the payment params directly. Sender, sending account address, signer, sending account signer, amounts, algo amounts. You can do something like 0.1. That should be sufficient. You'll probably use, like, depending on the structure of the boxes, the schema, up to 50,000 microalgo. So 100,000 is just a safe number. It has 6 decimals, so 0.1 is equivalent to 1 million microalgo. Receiver. This is going to be the slot machine client.app address, and of course validity window 1000, just to have it. And then params, default common app call params, send params, default send params. That's a transaction response. And up here, I'll just type creating user instance and slot machine. And down here, user instance created, transaction ID, transaction response dot transaction ID. Now let's test this out. Make sure it works. Looks good to me, but let's see. Yep, it's working fine. While that's running, we'll create a check user instances so we can take a look at the boxes that are there. To decode the box name and value, we'll need AVI types from the Algo SDK. So the box API type for the name, API type from string, and this doesn't need to be wrapped in a tuple, it could just be address. Box value, API type. It's very simple. API schemas, it's just a UN64. So boxes, algorand.app.get box names, app ID, we'll need from our constants. For box and boxes, box name is equal to the box name API type dot decode the box dot name raw value bytes, and then the box value. We can pass the API type for the box value directly when we get the box values at the same time. So you do get box value from API type, app ID, and API type. And we also need box name, actually. So box.name raw and box value API type. And we're going to print address, box name, chosen round, box value. And we should only get one coming out because we only called this once. So we have the address that I generated earlier. It has a chosen round 52,973,316. So it has surely been more than 8 rounds, for sure. The next VRF round has definitely passed. It's valid for 1,512 rounds, so we're still good. That's going to take an hour to pass and expire. So we have some time here to create our pull slot machine.py, slot machine clients, and what else do we need? I think that's it. Transaction response is equal to slot machine clients dot send full slot machine. There's no args. We do need these things again. App call, default send params. And we'll put here pulling slot machine lever. And here, slot machine lever pull. Transaction ID. The ABI return, so we'll need to access returns. And this will be an array of arrays. So if we want, we can create a hash map, well, fruit hash map. 0 will be apple. 1 will be peach. 2 will be banana. And what we'll do here is slot machine output. And we'll do fruit hash map, transaction, fruit hash map, index, for index in transaction response dot returns. Yeah. Maybe key would be better. And I think this should work. Just in case, I'm going to print transaction response dot returns. See the output. But we can run this now, I hope. Let's see. There we go. Pulling slot machine lever. And it's going to print the returns. Yep, that didn't occur the way I thought it would. Random output, API return, value. Key dot value. Yep, there it is. Key dot value for key transaction dot response. Dot returns. So each key is, yeah, no, that's not going to work. So we should do ABI return. Sorry, give me 1 second. These always confuse me. Fruit hash map key dot value for key in transaction response dot returns. Yeah, it wouldn't let me type dot value here if it wasn't appropriate, I'm hoping. So let me just create a new instance. And while we're here, we can check not the address, but the app ID. If we go to LoRa on testnet and we look at the application's address, the MBR is exactly where it needs to be. And this is after I created an instance. And hopefully this works fine. Pulling slot machine lever, unhashable type list. That's frustrating. I think I could just do 0. Yeah. I'm gonna just get the 0th index just to make sure I'm not crazy. But yeah, if I refresh here, it's 0.1, the exact account MBR. I just created another instance, it goes back up to 1185, same way it was. And it might be too early, let's see. Nope, we're good. And this is frustrating. Random output. Oh, I was looking at the wrong thing. So this is transaction.response.returns 0 dot value. Gotcha. So this is what this needs to be. And I pinky promise this is the last one. And we can just do this. All right. Cool. And we refresh. We're back to 1185 because we just created an instance. And let's see if the VRF is available. Looks like it is. Cool. So we got apple, peach, banana, 0, 1, 2. And that's pretty much it for the Python implementation. Sorry I got stuck here. Uh, list comprehension is sometimes tricky, especially when you have no idea what you're looking at. There's a lot of data, but we figured it out. And I'm going to end the video here. I guess I could get started with just in case like someone wants to get ahead of themselves. So it's I use Vite when I use React slot dash machine. Oof, almost hit pre-act. That would have been a GG. npm install. I'm just going to show you the libraries or the modules that you would need. So it's going to be npm install. You're going to need Algorand Foundation / AlgoKit utils. Para wallet / connect. Transaction labs / use wallet react. I also like to get both. Just regular use wallet. I feel like sometimes, I don't know, maybe this one's not necessary actually. And for the ABI types, if for whatever reason you want to display instances, you would need the Algo SDK. And for generating Algorand TypeScript client generator, yeah, here it is. So you would use this here. You can just Google what I Googled. I think I typed in Algorand TypeScript client generator. And this is the command here. And just to show you how I would change it, where is my terminal commands? Where did I put this? I'm blind, apparently. Maybe I didn't make one yet. I'll just make one now. Could have sworn I did this already. Let me just grab this. Install modules below for React. This is going to get you the wallet connections you need. generate TypeScript client for React. So this is the equivalent of what I typed earlier. I'll go hit compile. And then compile client from contract file, 6 file. It's going to be like this. And lastly, this. So you would need to contract files / slot machine 6.json. And out here, you'd maybe create a folder, slot machine, source. Yeah, why not? We'll just create clients, actually. Source clients. Slot machine client.ts. I'm assuming this will be fine and go in the correct place. It did not. Could not find application.json. That's because we don't need this. Could not find application.json. Slot machine.art56.json. Oh, we're not in the correct directory. So it's not interpreting it correctly. Yeah. So now we have a clients folder with our TypeScript client inside of our source folder for the React project. I'm going to end it here. It's getting too long, and maybe I'll create a second video for the front-end integration. Thank you, and good night.